Okay, in this lesson I'm going to go over the definition of continuity at a point. I'm going to expand that definition into continuity at an open interval, and then I'm going to go over some non-examples of both, getting more specific with the intervals with types of discontinuity. So we just finished talking about limits and how to find some limits analytically. Well, in that we can also have a function to be continuous, and there's three things that must be true for the function to be continuous. If f is your function, then it needs to be defined. For example, over here I have a sketch. This is where c is at. Notice it's closed there. There's a point. It is defined. So you cannot have that open circle like you sometimes see in those limits. But on the other hand, the limit as x approaches c of that function must exist. So what you see is, just like we've looked for limits graphically, as you approach c from both sides, it's getting closer and closer to that value. And number three, those values have to be the same. So whatever this is approaching on both sides, whatever the limit is, it has to be the same thing as the value at that point. If all three of those things hold true, then we say that function f is continuous at that point. So if c is 2, we'd say it's continuous at 2. Doesn't mean it's continuous throughout the whole function, just at that point. And just as important of knowing what the example looks like, non-examples are just as important. So down here I've showed you three possibilities that students sometimes get confused. I didn't show where it's unbounded, but of course any unbounded function at that point would be discontinuous at that point. In the first example, you notice that 1 and 3 fails. This is an example where the limit exists because it's approaching the same value from both sides. So when you were solving problems like number 2 earlier, you would say it exists and you have to find what that value at y is. But since both 1 and 3 fail, 3 has to fail because 1 fails. If f of c is undefined, there's no way it can equal the limit. So 1 and 3 fail. For number 2, this time you have a situation where it's defined, that's that closed circle there, but it's approaching a different value on the left than it is from the right. So therefore, the limit does not exist. And if the limit does not exist, again, there's no way the two can be equal. So it fails. You can have a situation where it's defined. That's the dark circle there. The limit exists. It's approaching a value from both sides, but those two values are not the same for C. So it fails because number 3 fails. Expanding on that idea of a point, we have what is called continuity on an open interval. So all you're doing when you do an open interval is you're checking every point from A to B, and if all those things hold true for each point, those three things, then you can say not only is it continuous on a point, you can say it's continuous on an open interval. Now, sometimes students get confused. They say, well, do these have to be open? Well, no, not really. You know, if it's closed, you might be able to make the open interval farther. But when you make it an open interval, then you can definitely say the largest open interval, which is negative infinity to infinity, you can have it. If you force it to be a closed interval, then you can't talk about this situation. And if the open interval happens to be negative infinity to infinity, for example, y equals x squared, that parabola goes all the way from negative infinity to infinity, and every point on that interval holds as far as continuity is concerned, then you can say the whole function is everywhere continuous. To show you some non-examples, and also there's some important terms with the non-examples. Here you have what is called a removable discontinuity at C. And what that means is if you could redefine C, in fact, if you could just fill in that circle at C, then it ends up being continuous throughout that open interval. So it only takes a redefining of C, and this would change from discontinuous to continuous. On the next one, it's the same thing, because even though you have a closed circle above it, if you change that and you're able to make the closed circle there instead, just read and everything else stay the same, then you have a continuous function from a to b. So therefore, because it only takes the redefining of c to change this, we call that a removable discontinuity at that value. Down here on the other hand, at c, here you have some unbounded things. It doesn't matter what you redefine c as, there's no way it can be continuous at c. So we call that a non-removable discontinuity. And the same thing holds true here. Sometimes this is a little more confusing. You could move this up here, but still the limit would not exist at c, which is one of the criteria for that. So that would be a non-removable discontinuity, because no matter where you move this value to change f of c, there's no way you can make it continuous.